In this presentation, we're going to show our work on direct force imposed nonlinear NPC with multiple interaction modes for aerial push and slide operations. In recent years, microaerial vehicles, or MAVs, have increasingly been used for aerial interaction. Aerial interaction can comprise a wide variety of tasks, such as pick and place of objects, pushing and sliding along a surface, or active manipulation of the environment. Depending on the desired interaction task, the flying platform needs to meet certain actuation requirements. While pick-and-place tasks can be achieved by classical under-actuated MAVs, other interaction tasks often require over-actuated systems. Over-actuation allows the platform to follow a post trajectory while simultaneously applying interaction forces. In our work, we're focusing on aerial interaction with over-actuated MAVs, using a model-based control approach. Earlier works have already analyzed control methods for interaction of over-actuated MAVs. On the left, you can see a hexarotor equipped with a 2 degrees of freedom arm whose end-effector can stay in contact while sliding along a metallic pipe. The over-actuation of the hexarotor is achieved by tilted propellers, and it allows to compensate for contact forces while being in contact with the surface. On the right, another fixed tilt platform allows for peg-in-hole operations as well as simultaneous pose and wrench control while in contact with another surface. So far, most works rely on impedance controllers. While these allow the platform to establish and maintain contact for most tasks, they don't take into account forces and torques that arise at the contact point. This can specifically get challenging in more complex interaction tasks. This is where model predictive control, or NPC, can provide advantages. By incorporating our knowledge about the system dynamics in the controller, we can find optimal control inputs according to a specifically designed cost function. On the left, you can see an example of where NPC has already been applied on aerial righting with an under-actuated hexarotor in combination with a delta arm. In one of our earlier works, we have already used NPC to incorporate the model dynamics of an over-actuated MAV while tracking trajectories with 6 degrees of freedom in free space. In this work, we would like to achieve the following. First, we want to track a pose and a force reference during a push and slide task on a plane surface. Second, we want to fuse the measurements of a force torque sensor at the end effector to achieve direct force control. Third, we want to apply principles of friction physics to model the interaction in the NPC. And fourth, as the interaction dynamics naturally change during the task execution, the controller should autonomously detect the current stage of the task and adapt the NPC model accordingly. Looking at the different stages during a push and slide task, we find 3 different stages. First, free flight, when there is no contact between the OMAV and the environment. Second, static interaction, when there is contact but the end effector is not moving. In this situation, static friction or stiction prevents the end effector from moving laterally. And then third, dynamic interaction, when the end effector is sliding along the surface of the wall. In this stage, dynamic friction is acting between the end effector and the wall. Having defined these 3 stages, the main challenge lies in autonomously detecting the current stage and adapting the controller accordingly. Based on the 3 identified flight stages, we define the corresponding flight modes: free flight, static force control, and dynamic force control. Depending on the flight mode, we control only the pose of the platform or both the pose and interaction force. At the same time, we use the information about the flight mode to change the interaction dynamics in the NPC. In order to detect and to switch between interaction modes, we use 2 selection factors. The first selection factor lambda distinguishes between free flight and interaction. It detects interaction if 2 conditions are met. First, the measured contact force has to be above a threshold, and second, the position error projected onto the reference contact force has to be below a threshold. This latter condition ensures to detach from the surface once the interaction task has finished. If one of the conditions is not fulfilled, the platform is supposed to be in free flight. The second selection factor, sigma, distinguishes between static and dynamic force control. It detects dynamic, so sliding, force control if the measured friction force is below a threshold or if the reference velocity is above a threshold. This is based on the assumption that dynamic friction forces are generally lower than static friction forces. All mentioned thresholds are tuning variables and depend mostly on the materials of the surface and the end effector. Now that we have defined the interaction modes, we can define the NPC problem. The states in NPC are made up from the wrench, so the force and the torque that is generated by the actuators that the platforms pose and its derivatives. The inputs that we optimize over are the time derivatives of the actuator wrench. This is helpful as we can constrain the wrench rates according to physical limitations. Finally, the cost vector h includes both the pose error as well as the force tracking error at the end effector. We use the information of the flight mode to adapt the system dynamics and the weight matrices Q and Qn in the cost function. That way, we set the cost on the force tracking error to 0 when the platform is in free flight. Next, we're going to show results of experiments we have done in our lab at ETH Zurich. We used a custom-built over-actuated MAV that includes 6 individually tiltable arms with coaxial double rotor groups. We've attached a rigid arm with an interchangeable end-effector. Between the arm and the end-effector, a force-torque sensor gives us real-time measurements of the wrench acting at the tip of the arm. The entire system, including its 2 onboard batteries, has a weight of approximately 5 kilograms. For state estimation, we use a Vicon motion capture system in combination with an onboard IMU. The NPC calculations are performed by an onboard Intel NUC, and the commands are forwarded to the actuators through a Pixhawk flight controller. We've used a customary whiteboard as an interaction surface. We did experiments with 2 different end effectors, one being a rubber ball providing high friction, and the other one being a whiteboard marker with low friction. First, we'll show the result of the experiment with a high friction end effector. The top plot shows the evolution of the selection factors lambda in red and sigma in black during a horizontal push and slide task. The 3D plot on the right shows the reference interaction force as a light red arrow as well as the measured interaction forces at the end effector. Before the start of the interaction, lambda is 0, meaning that the MAV is in free flight. Once contact is established, lambda switches to 1 and therefore determines interaction. While the MAV is hovering in front of the whiteboard, sigma switches from 1 to 0, therefore detecting static force control. Once the horizontal traverse is commanded, sigma switches to 1, changing the interaction mode to dynamic force control. After the horizontal traverse, the mode switches back to static force control again, as can be seen by sigma going back to 0. Next, we show the result of the experiment with a low friction end effector. As before, lambda automatically switches from 0 to 1 once interaction is detected. Shortly after, sigma switches to 0, determining static force control. During the horizontal traverse, sigma switches back to 1 to indicate dynamic force control. However, shortly after the traverse, sigma again approaches dynamic force control for a brief moment. This is a result of inaccurate tuning of the lateral force thresholds. After that, it again correctly determines static force control before traversing back to the right. To sum up our work, we have implemented and evaluated an NPC framework that incorporates different stages during a push and slide task. The model as well as the tuning of the controller is adapted automatically by detecting the current interaction state. This interaction state is determined by selection factors which are computed based on sensor measurements. First experiments showed that automatic switching of the interaction modes worked in both high and low friction scenarios. However, we noticed that specifically nonlinear effects in high friction interaction experiments remained a difficult challenge. A more sophisticated modeling and proper identification of the interaction dynamics will probably still improve the performance of the controller. Thank you for listening, and I'm happy to answer your questions.